Welcome to the clickmyproject.com. This is our project title, Compact DFA Scalable Pattern Matching using Longest Prefix Match Solutions. This is abstract of our project. The pattern matching is the act of checking a given sequence of tokens for the presence of the constants of some pattern. A central component in all contemporary intrusion detection systems is the pattern matching algorithms, which are frequently centered on creating and traversing a deterministic finite automation. It is nothing but defining as a DFA that signifies the pattern. While regular DFA stores separately each transition between two states, we use this degree of freedom and encode states in such a way that all transitions to a specific state are represented by a single prefix that defines a set of current states. Here we are going to perform the pattern matching process by the longest pattern matching solutions. A PCAM skin can reach a throughput of 10 GB with low power consumption. Our main process is a intrusion detection system. We are going to identify the data transmission in the network. Though this method guarantees deterministic time guarantees, modern intrusion detection system need to deal with the hundreds of patterns. The patterns is nothing but the node identification, thus needing to store very large DFAs, which frequently do not fit in fast memory. This outcomes in a major bottleneck on the throughput of the IDS, as well as its power consumption and cost. Here we propose a novel model to compress the DFA by observing that the name used by the common DFA encoding is meaningless. Here the DFA construction is based on the number of nodes present in the network and based on the data transmission in the network. This is the DFA of our process. Here we load our input. The input contains nothing but the information of the source node and destination node and some of the process and the data we are going to transmit in the network. After that, the input collection, we convert that information into the states. The state representation is nothing but in the form of S0, S1, S2, S3 up to the number of informations present in our data set. After the state conversion process, we are going to perform the pattern generation. We are going to generate the patterns using the regular expression. After the pattern generation process, we are going to identify the pattern recognition, whether they are given input present in the form of the regular expression. After that, we perform the state grouping process. After the state grouping process, we are going to perform the suffix tree construction. The suffix tree construction is nothing but we are identifying the some of the informations present in our input data set. Based on the suffix tree construction, we perform the rule encoding process. The rule is nothing but identifying the previous state and the next state and what we are going to perform and encode the rules in a unreadable form. After that, we show the output rules. And based on the rules, finally we show our compressed DFA results, which contain the source state and destination state and what is the next state, how we represent it. Let us see the demo of our process. Just open the NetBeans and the title name Compact DFA. In the Compact DFA, we just run the home page. It is our process. Right click the homepage.java. Our home page appears. In the home page, we just enter into the process. Here we are going to load the data set. The data set is nothing but our input data, which is transferred in the network. You can able to choose any data set. These are the informations present in our data set. Then next. Here we select the formatted data, which is our input data. So we select the process.txt and it is the length of the data set. Then we are going to perform the state generation process. Generated successfully. The state representation is nothing but in the form of S0, S1, S2 up to the how much information is present in our data set. These are the state representation of our input data set. Then next, this is a tree construction. The root node is the first state and the siblings are the remaining states. Then Next. Then we are going to perform the pattern generation process. The pattern generation process takes place using the regular expression. The regular expression is generated based on the information present in our input data set. Generate patterns are generated successfully. View patterns. These are the pattern representation of our data present in our data set. Then we are going to perform the suffix tree construction. The suffix tree construction takes place from the pattern generation process. From the patterns, we are going to split the suffix informations of the each and every data present in our data set. So process. Then view suffix tree data. These are all the suffix informations of our data set. These are all the first data suffix details, second data suffix details, etc. Up to all, for all data it shows the suffix informations. Then here we show the suffix tree formation. This is a suffix root node for the first state, second state, up to all the states present in our process. Finally, we are going to perform the rule encoding process. First of all, we are going to generate the rules. These are the original data where we are going to apply the rules, and we are going to generate the general rules for all the data which we converted into the patterns using the regular expression. Then encoding process takes place. Rule encoded successfully. Finally, it shows the rules. It contains information like what is the current state, how we are going to represent it, what is the next state, with the state representation with binary, that is the rule representation also. This is a performance evaluation. First one is a memory consumption. Here we perform the DFA, that is a compressed DFA. In the existing approach, they use the AG-NFA. In the NFA process, it contains more memory to store all the informations which travel in the network. But in our process, in the DFA process, it contains less memory to store all the informations which travel in the network. First. Then execution time. The execution time is evaluated based on the length of the pattern. In the existing system, if the length of the pattern is increased, the execution time also get increased. But in the proposed approach, not like that. If the length of the pattern get increased, the execution time is reduced compared to the existing system. We check the results in our network also. For that, we just right click the user information and run. In this, should enter the sender ID, sender IP, then select the sender data and store the information. Then click next. Here we are going to convert our data which is going to transfer in the network into a patterns, and it is a generated pattern. Then here we are going to enter the port number, then trigger. Then we should separately run the client.java. In that, we should enter the local host, because we run both our server and client in the same process. We connect the two systems within a single system. So enter the same port number. Then request. Then it sends the data. It receives the response from the server. Then it should enter the receiver ID and receiver IP. Then store the information. After that, we convert the data which is received by the receiver into the patterns, the pattern information. After this pattern generation, we are going to check during the transmission in the network whether any loss in the data or any modification or any data corruption in data. Further, we perform the pattern matching process. The pattern matching process, the original data is received. There is no modification in it. So finally, the graph is shown. The execution time. This is a comparison of the pattern matching of the compact DFA with the nodes system. It is a proposed node. Then the first takes the high execution time compared to the second one. Second, data loss. Data loss in terms of percentage. Compact DFA, the data loss is high. In North or Spread DFA, the data loss is less. Thank you.